All right, let's jump straight into this explainer. Today, we are unpacking the incredibly dense but absolutely fascinating I-S3 JC-STAR in-depth investigation report. Look, if you're working in the distributed energy space, you already know Japan's new cybersecurity rules are completely shaking up the industry right now. What we're doing today is moving past the wild industry rumors to look strictly at the verified, on-the-ground realities of the JC-STAR certification system. We're going to explore what these new grid connection requirements actually mean for system designers, what glaring gaps exist in the current framework, and most importantly, how we can achieve true resilience.
Here is our roadmap for today. We'll start with a reality check on JC-STAR, explore the rather strange wind versus solar asymmetry, and unpack the static certification trap. Then we'll dive into the OEM transparency problem, introduce the LEAA solution, and finally discuss why physics ultimately beats certification. Let's get right into it.
Part 1. The JC-STAR reality check. Let's establish the facts.
So, to really understand this investigation, we need a factual baseline of the new grid connection requirements. It's totally crucial to understand exactly what is being asked of the industry, and just as importantly, when these rules actually kick in. These are the hard deadlines derived straight from the Grid Code Study Group. This establishes exactly when JC-STAR compliance becomes non-negotiable for new grid connection applications. If you're dealing with high-voltage solar or battery energy storage systems, your clock strikes in April 2027. For low-voltage systems, the ones under 50 kilowatts, you get a tiny bit of breathing room until October 2027 to let existing inventory clear out. And for fuel cells, your deadline is April 2028. The timeline is seriously tight, and the impact is going to be massive.
Get used to the Level 1 JC-STAR label. Spearheaded by the Information Technology Promotion Agency, or the IPA, this specifically targets the absolute minimum cybersecurity hygiene for IoT products. We're talking about basic foundational stuff here. No default passwords, basic authentication functions, and having clear vulnerability response contacts. It is a necessary first step for securing the grid.
Now, here's where things get interesting, because there is a major misconception out there. A lot of people think JC-STAR is just a simple self-declaration system. Check a box and you're good, right? Well, the report uncovers a hidden reality. It actually involves a rigorous, non-public screening process by both the IPA and the Ministry of Economy, Trade, and Industry before an application is even accepted. Applications absolutely can be rejected. Furthermore, while the label guarantees that minimum hygiene, the IPA explicitly states it does not guarantee complete security, especially if you're dealing with intentional backdoors or dynamic configuration changes once the equipment is actually running in the field.
Moving on to Part 2, wind versus solar asymmetry, because, as it turns out, the rules aren't exactly uniform.
You'd logically assume the grid treats all distributed energy resources equally, right? Power is power. But the source material reveals this fascinating split depending on how you actually generate it. The really crucial point here is the stark contrast in trust boundaries. If you're building a solar plant, the regulations force you to get product-level certification for deep internal equipment, like your power conditioning systems and your energy management systems. But if you're building a wind farm, certification only applies to boundary devices, like your gateway firewalls. It's a completely different approach.
So why the special treatment for wind? Well, the Grid Code Study Group documents make it clear that this exemption isn't based on some brilliant architectural risk assessment. It's actually just a compromise based on supply chain feasibility. Wind turbines are packed with foreign-made IP devices, and forcing every single one of them to get JC-STAR certified all at once was deemed way too difficult and time-consuming. So wind power inadvertently scored a boundary-only approach, which is actually much closer to international IEC 62443 standards, while solar is stuck certifying every internal component.
Which brings us to Part 3, the static certification trap. Let's talk about what happens when things change.
Next, we're exploring our really fundamental gap identified in the report. It's the physical reality of running a dynamic power plant versus the totally static nature of a certification label. Think about it. What actually happens to your compliance when the network dynamically changes during operation? A power plant is not a smartphone that stays exactly the same after you take it out of the box. Adding an LTE router, swapping out a monitoring device, or even just temporarily connecting a maintenance PC changes the on-site reality completely. A static certification label slapped on at the factory just doesn't account for these real-world, dynamic network changes.
This quote from a legal analysis in the report really hits the nail on the head regarding a massive vulnerability in this framework. There is literally no mechanism right now to track network configuration changes after day one. What the guidelines do say is that replacing existing equipment triggers the new requirements. This means a single replaced inverter unit, maybe it just broke and you swapped it, could trigger a massive compliance cascade. forcing the entire power plant to suddenly require full JC-STAR conformity. It's a logistical nightmare waiting to happen.
Part 4. The OEM transparency problem, or trying to separate fact from industry fiction.
Let's put on our investigative hats for a second. There is a ton of wild industry chatter out there, so the I-S3 report rigorously cross-checked these rumors strictly against public information. The rumor that all overseas brands are just flat-out excluded? Totally false. Companies from Germany, Spain, and Taiwan have already passed. Now, it is a fact that Huawei has not been confirmed under its own brand name. However, and this is a huge finding, domestic OEM brands that use Huawei equipment under the hood are absolutely in circulation and have easily obtained certification. And finally, because the application process is completely confidential, there is zero public way to know if a company applied and got rejected, or if they just chose to apply through a domestic partner instead.
So why is everyone guessing? Why are these rumors so rampant? It all boils down to where the trust boundary is drawn. Because the public list only shows the applicant, like a domestic Japanese sales brand, and completely hides the original manufacturer, it creates a massive information asymmetry. The IPA knows who the real manufacturer is behind the scenes, but the public doesn't. And that lack of transparency is exactly what breeds these unverifiable industry rumors about certain companies being locked out, when in reality, their tech is likely just passing through a domestic OEM applicant.
All right, part 5. Enter the LEAA solution. Let's talk about some actual architectural resilience.
So, if a static digital label has all these dynamic blind spots and transparency issues, how do we actually physically secure the grid? The source material proposes a really compelling alternative framework called LEAA. That stands for Load Equivalent Autonomous Resilience Architecture. It's designed to protect the grid through physical separation, rather than relying purely on software certification. The core idea here is that certification is a great starting point, sure, but architecture is what actually saves you when the software eventually fails.
Here's how LEAA works in 3 foundational steps. Step 1 is the complete separation of logic and physics. You literally put a physical air gap between the IT network and your physical power protection relays. Step 2 is load equivalence. By using hardware to physically block reverse power flow, the facility just looks like a normal, harmless load to the wider grid. It can't push bad power back up the line. And step 3 is autonomous degradation. If the cloud goes down or you get hit by ransomware, it doesn't crash the grid. The system just safely islands itself and keeps critical local loads running independently. Even if the software layer is 100% compromised, the physical layer stops the attack cold.
Finally, part 6. Physics over certification. Let's get into some actionable takeaways.
So how do system designers and facility managers actually build this out? By adhering to this compliance checklist, designers can utilize a powerful yes and approach. Yes to getting the initial JC-STAR certification, absolutely. And yes to implementing physical protection layers like EAA. You need hardware-based reverse power flow prevention. You have to ensure the protection settings absolutely cannot be rewritten over a network connection like Modbus. It's about acknowledging that while stronger regulation is definitely necessary, regulation and certification alone just aren't enough to ensure true resilience. I am going to leave you with this provocative thought straight from the source material. Just because a device is certified doesn't necessarily mean the system as a whole is safe. That weird mismatch between the wind and solar regulations we talked about, that shows us that boundary defense is actually incredibly effective. So instead of just obsessing over which individual product we're certifying, perhaps the industry needs to focus heavily on where we draw the physical trust boundary in the first place. Something to definitely think about. Thanks so much for joining me on this deep dive explainer.